Okay, let's go. Number 1. Rotating Universe. The year is 1949. You're Kurt Gödel, 43 years old, one of the greatest logicians who has ever lived, and you're standing at a blackboard in the Institute for Advanced Study in Princeton, New Jersey, about to deliver a birthday present that will disturb the most famous physicist on Earth. The occasion is a seminar honoring Albert Einstein's 70th birthday. Einstein is in the room. He's been your close friend for years, your walking companion on the daily route home from the Institute, the man who once told a colleague that he came to work only to have the privilege of walking home with Gödel. You aren't here to celebrate him. You're here to show him something his own equations permit that he desperately hoped they wouldn't. The paper you present that day, published later that year in Reviews of Modern Physics, Volume 21, page 447, describes a solution to Einstein's general relativistic field equations. The solution is exact. It is mathematically rigorous, and it describes a universe that contains closed, time-like curves, paths through space-time that loop back on themselves, trajectories a traveler could follow and arrive at a point in their own past. In Gödel's universe, filled with uniformly rotating matter and no expansion, time travel isn't speculative. It's permitted by the geometry of space-time itself. This was the first valid time machine solution in the history of physics. Not a thought experiment, not a philosophical argument, not science fiction dressed in equations. Gödel had derived a proven solution to the foundational equations of general relativity and presented it directly to the man who wrote those equations. Einstein didn't celebrate. He was deeply disturbed. He had spent decades hoping that general relativity, whatever else it allowed, would preserve a clear distinction between past, present, and future. Gödel had just shown, using Einstein's own mathematics, that no such distinction was guaranteed. The equations that described gravity, space-time, and the structure of the cosmos also permitted a universe where a sufficiently determined traveler could visit yesterday. Philosopher Palle Yorgrau, who documented the intellectual aftermath in detail, described Gödel's result as a bomb lobbed into the foundations of physics. Yorgrau also documented what he called a conspiracy of silence that descended on the result in the years that followed. The physics community did not refute Gödel's solution. They couldn't. The mathematics was correct. They simply stopped talking about it. But the silence didn't make the problem disappear. Gödel's solution has never been retracted, never been shown to contain an error, never been withdrawn from the literature. It sits in Reviews of Modern Physics, exactly where Gödel left it in 1949, intact, valid, unchallenged on its own terms. What stopped it was the universe itself. Gödel's solution describes a cosmos filled with rotating matter. Our universe doesn't rotate, it expands. The astronomical observations that accumulated through the second half of the 20th century confirmed an expanding universe with no detectable global rotation, which means Gödel's solution, while mathematically perfect, describes a universe that isn't ours. The time machine works, it just works somewhere else. That should have been the end of the story. It wasn't, because what Gödel had proven wasn't that time travel exists in our universe. He had proven something more dangerous, that general relativity, as a mathematical framework, permits it. The equations don't forbid a traveler from reaching their own past. If our particular universe doesn't allow it, that's a contingent fact about the arrangement of matter and energy, not a fundamental law. The question shifted permanently after that Princeton seminar. It was no longer, is time travel possible? It became, what additional constraints, beyond Einstein's equations, does nature impose to prevent it? Gödel was the first person to ask that question with a valid proof in hand. He wasn't the last. Over the following 75 years, 10 separate groups across 3 continents, physicists at major universities, a NASA lab that accidentally discovered a warp bubble, a collaboration of 174 physicists who measured neutrinos arriving faster than light, a Soviet aerospace engineer who built a prototype and measured time slowing down inside it, got far enough to publish proofs, build prototypes, or run experiments aimed at manipulating the structure of time. Every single one was stopped. Different mechanisms, different decades, different countries, same result. They stop. Why does every attempt to build a time machine get stopped before it finishes? Gödel proved time travel was mathematically possible, but he never proposed building a machine. He was a logician, not an engineer. His interest was in what the equations permitted, not in what the physical world could deliver. 42 years later, a Princeton astrophysicist published something in Physical Review Letters that took Gödel's permission slip and turned it into a blueprint. The mechanism he proposed required objects so exotic they might not exist anywhere in the observable universe, enormous filaments of energy left over from the Big Bang, hurtling past each other at nearly the speed of light. Whether those filaments are real is still an open question. What the astrophysicist showed they could do, if they are, changed the conversation again. Number 2. Cosmic string time machine. Gödel proved the math permitted time travel, but he never said how to build one. He showed that general relativity allowed closed time-like curves in a rotating universe, and he stopped there. The proof was elegant. It was also useless, because nobody could point to an object in the actual universe and say, that's the mechanism, 2 of those, moving fast enough, and you've got a time machine. In 1991, a Princeton astrophysicist did exactly that. The year is 1991. You're J. Richard Gott III, professor of astrophysics at Princeton University, and you've just submitted a paper to Physical Review Letters that identifies a specific object, something the early universe may have produced, that could bend spacetime into a closed loop. The object is a cosmic string. Cosmic strings are hypothetical one-dimensional defects in spacetime, remnants from phase transitions in the first fractions of a second after the Big Bang. Think of them as cracks in the structure of the universe, frozen into existence as the cosmos cooled. They're enormous filaments of concentrated energy, thinner than an atom but potentially stretching across the entire observable universe. A single inch of cosmic string would weigh about 10 million billion tons. That's the mass of Mount Everest compressed into something narrower than a proton. Gott's paper, Closed Time-like Curves Produced by Pairs of Moving Cosmic Strings, appeared in Physical Review Letters, Volume 66, page 1126. The mechanism was specific. Take 2 infinite cosmic strings hurtling past each other at velocities approaching the speed of light. A traveler following a precise figure-8 path around the separating strings would arrive back at their starting point before they left. Not by exploiting a wormhole or spinning an infinite cylinder, but by flying a carefully calculated trajectory around 2 objects whose gravitational effects on spacetime are so severe that the normal relationship between departure and arrival breaks down. The mechanism relied on gravitational lensing and the relativity of simultaneity, purely general relativistic. No exotic physics required beyond the strings themselves. Time magazine ran a cover story on time travel that year, featuring Gott's work. A Princeton astrophysicist in Time magazine, explaining to millions of readers how 2 cosmic strings could send you to the past. But Stephen Hawking was paying attention. Hawking responded directly. He examined Gott's cosmic string scenario and proved that if the strings were finite in length, which any real object would have to be, they could not create closed, time-like curves. Only infinite strings would work. Strings that stretch forever in both directions with no endpoints. An infinite string isn't an object you can find or manufacture. It's a mathematical abstraction. This became part of Hawking's broader chronology protection conjecture, published in 1992. The argument that the laws of physics conspire to prevent time machines from forming. Gott had identified the mechanism. Hawking had identified the lock. And there's a more fundamental problem. No cosmic string has ever been detected. They're predicted by certain models of the early universe, by some grand unified theories, and by cosmic inflation scenarios. But after decades of searching through gravitational lensing surveys and cosmic microwave background data, no observational evidence for cosmic strings has been found. Gott's time machine requires 2 objects that may not exist, traveling at speeds that may not be achievable, with lengths that can't be finite. The blueprint is valid. Every component of the hardware is missing. Gott didn't stop there. In 1997 and 1998, he collaborated with Li-Shin Li on what may be the most audacious paper title in the history of physics. Published in Physical Review D, it was called Can the Universe Create Itself? Their model proposed that the universe could be its own mother, that a closed time-like curve loop in the early cosmos could have allowed the universe to bring itself into existence. It didn't need a first cause, because it was its own first cause, looping back through time to create the conditions for its own Big Bang. Gott later wrote the popular book Time Travel in Einstein's Universe, published in 2001, laying out the full landscape of time travel physics for a general audience. But Gott's cosmic strings required objects that might not exist anywhere in the observable universe, And he wasn't the first physicist to submit a time machine to a peer-reviewed journal and have it published. 17 years before Gott's paper, a mathematician at Tulane University in New Orleans submitted a proof to Physical Review D showing that a specific configuration of spinning matter would create closed, time-like curves. The referees reviewed it. They couldn't find the flaw. And when the journal published it in April 1974, it forced a response from the most famous physicist alive. Number 3. Rotating cylinder. The year is 1974. You're Frank Tipler, a young mathematician at Tulane University in New Orleans, and you've just submitted a paper to Physical Review D with a title that sounds like it belongs in a science fiction novel. Rotating cylinders and the possibility of global causality violation. Causality violation, that's the physics term for what everyone else calls time travel. And you've just submitted a mathematical proof that it's possible to the same journal that published Einstein. The paper passed peer review. The referees couldn't find the flaw because there wasn't one. Physical Review D published it in April 1974, Volume 9, Number 8, pages 2203 through 2206. 4 pages. 4 pages that proved, within the framework of general relativity, that a specific configuration of matter could bend spacetime into closed time-like curves, a path through spacetime that loops back on itself. Travel along that path and you arrive at the point you departed from, at the time you departed from. A loop in time, not in space. The configuration Tipler described was specific, an infinitely long cylinder of infinite density, spinning at billions of rotations per second. The rotation would drag the surrounding spacetime with it, a phenomenon called frame dragging that general relativity predicts, and that has since been measured by the Gravity Probe B satellite in 2011. At sufficient rotational speed and sufficient density, the frame dragging becomes extreme enough to twist spacetime into those closed curves. Time bends. The loop opens. The math was clean. The derivation was correct. The problem was the materials. The cylinder would require mass equal to approximately 10 solar masses compressed into a structure of infinite length. There is no material in the known universe that can withstand rotational forces at billions of revolutions per second. The density required is beyond neutron star matter. The length required is beyond the observable universe. Every physical requirement of the design exceeds every physical capability of any technology, any material, any energy source available to any civilization that has ever existed on this planet. This decision seemed small at the time. It wasn't. The editorial board of Physical Review D accepted the paper, and in doing so, they made time travel a legitimate subject of mainstream physics. It wasn't fringe anymore. It was published, peer-reviewed, and sitting in the same journal that carried foundational work on general relativity. That legitimacy forced a response from the top. The response came from Stephen Hawking. In 1992, 18 years after Tipler's paper, Hawking published the chronology protection conjecture. The argument was elegant and absolute. Hawking proposed that the laws of physics themselves, specifically the behavior of quantum fields near the boundary of a closed time-like curve, would prevent any time machine from forming. The laws of physics are the enforcement mechanism, and they activate automatically the moment a time machine comes close to forming. Hawking went further. He conducted what he called an experiment. On June 28, 2009, he hosted a champagne party for time travelers at the University of Cambridge. He set the table, opened the champagne, and waited. He had sent no invitations in advance. The invitations were printed and distributed after the party was over, with the exact coordinates and time of the event. His reasoning was that if time travel would ever be possible at any point in the future, someone would have received the invitation in their past, traveled back to 2009, and attended. Nobody came. He threw a party for people from the future and sent the invitations afterward. Nobody showed up. He published the empty guest list as experimental evidence that time travel is not possible. That's the kind of experiment you can only design if you're Stephen Hawking. Tipler's paper is still published. It has never been retracted. The math has never been disproven. Hawking's conjecture remains a conjecture, not a theorem, because no proof of it exists either. The cylinder works on paper. The universe, according to Hawking, will not let you build it. If you're enjoying this, subscribe so you don't miss the rest of this list. The next 7 get stranger. Hawking declared time machines permanently impossible. But 4 years before he published that conjecture, the paper that forced him to respond had already been submitted. A Caltech physicist got a phone call from a science fiction novelist who needed help with the plot of a book. The physicist produced 50 lines of equations to help the novelist, and in the process, he designed the most complete time machine blueprint in the history of physics. It was published in Physical Review letters. The editors accepted it. The referees couldn't find a flaw. And then the physicist's own analysis revealed something about the design that no civilization on Earth could solve. Number 4. Wormhole Time Machine. The year is 1985. You're Kip Thorne, professor of theoretical physics at Caltech, and the phone is ringing. On the other end is Carl Sagan, the astronomer, the author, the man who made the cosmos a household conversation for 500 million television viewers. Sagan is writing a novel called Contact. He needs his protagonist to cross the galaxy, and he needs the physics to hold up under scrutiny. He asks you, his friend, to check his homework. You sit down with a legal pad and work through the problem. What comes out isn't a plot device. It's 50 lines of equations describing a traversable wormhole, a tunnel through space-time connecting two distant points through a shortcut so compressed that a journey of light years reduces to a walk of a few feet. Sagan gets his novel. You get something no one expected from a favor for a novelist, a working time machine blueprint. 3 years later, in 1988, you co-author a paper with Michael Morris and Ulvi Yurtsever. The title is Wormholes, Time Machines, and the Weak Energy Condition. You submit it to Physical Review letters. PRL doesn't accept speculative work. It doesn't publish thought experiments. Every paper in PRL has survived a peer review process that kills most submissions before they reach print. Your paper survives. Volume 61. Number 13. 1988. Pages 1446 through 1449. 4 pages. Published in the same journal that carried Einstein's work on the photoelectric effect, Fermi's work on beta decay, the discovery of the W and Z bosons. And now, sitting between papers on quark interactions and gravitational lensing, a complete theoretical blueprint for a machine that moves people through time. The design is specific enough that an engineer could sketch the components. Take one mouth of the traversable wormhole and accelerate it to near light speed using some form of propulsion, then return it to its starting position. Time dilation, the relativistic effect Einstein described and that GPS satellites correct for every day, means the accelerated mouth has experienced less time than the stationary mouth. The two ends now sit at different points in time. Walk through one side, emerge from the other side at a different moment. Not a different place, a different when. The wormhole doesn't move you through space, it moves you through time. The physics community didn't dismiss it. They couldn't. Kip Thorne was already one of the most respected relativists alive. He'd co-authored the definitive graduate textbook on general relativity with John Wheeler and Charles Misner. His work on black holes and gravitational physics was foundational. PRL's editorial board published it because the math was correct, and the referees couldn't find a flaw. For a brief period in 1988, the most credible time machine blueprint in physics sat in a peer-reviewed journal, available to anyone with a library card. Then the stop came, and it came from Thorne's own analysis. The traversable wormhole at the center of the design required one thing that no laboratory, no accelerator, no engineering project on Earth could provide: exotic matter. Specifically, matter with negative energy density, a substance whose energy content is below that of completely empty space, a material that would exert gravitational repulsion rather than attraction. No known substance has this property. Not rare, not expensive, not hard to produce. It simply doesn't exist. Without exotic matter threading the wormhole's throat, the tunnel collapses before anything can pass through. General relativity allows the wormhole. Quantum field theory doesn't supply the material to keep it open. Thorne shifted his focus to gravitational wave detection, the project that would consume the next 3 decades and eventually earn him the Nobel Prize in 2017 for the direct observation of gravitational waves by the LIGO detector. He shared the prize with Rainer Weiss and Barry Barish. The wormhole paper sits in PRL, unretracted, unrefuted, and unbuildable. A Nobel laureate's blueprint, locked behind a substance the universe has never provided. Every time machine so far has required something impossible: infinite cylinders, cosmic strings, exotic matter. But while the theorists were proving what couldn't exist, a physicist at the University of Connecticut was ignoring all of them. He'd been trying to build a time machine since he was 10 years old, since the day his father dropped dead of a heart attack at 33 in front of his family, and a boy standing in the back of the room decided he was going to build a machine to see him again. His name was Ron Mallett. He is still trying. Number 5. Ring laser time machine. The year is 1955. You're 10 years old, standing in a room in the Bronx, and your father is dying. Boyd Mallett, 33 years old, heavy smoker, drops from a heart attack in front of his family. The boy standing in the back of the room doesn't cry the way his siblings cry. He goes quiet. Something shuts down inside him and something else starts running, a question that won't stop. Can he get his father back? Within the same year, the boy finds a copy of The Time Machine by H.G. Wells at a bookstore. He reads it in one sitting. The idea doesn't hit him as fiction, it hits him as a possibility. A machine. You build it. You go back. You warn your father. You save him. That boy was Ron Mallett. And from that moment forward, every academic decision he made, every class, every course, every thesis, every research program was pointed at one thing. He enrolled at Penn State. He studied physics. He earned a doctorate. He joined the faculty at the University of Connecticut as a theoretical physicist. He told no one about the real reason for his career choice for decades, because he understood what would happen to his credibility if he said it out loud. A black physicist in a department where he was already the minority, telling colleagues that his life's work was building a time machine to save his dead father. He kept it quiet, and he kept working. The physics he developed was real. Mallett derived equations based on Einstein's general theory of relativity, showing that a circulating beam of laser light could produce frame-dragging effects. Frame dragging is the phenomenon where a massive rotating object pulls the fabric of space-time around with it, like a spoon twisting honey. Einstein predicted it. NASA's Gravity Probe B confirmed it in 2011. What Mallett proposed was that light itself, under the right conditions, could produce a version of the same effect. Circulating laser light, arranged in a ring, could twist space-time enough to create a closed time-like curve, a loop in time. He built a tabletop prototype, a ring laser demonstrating frame-dragging effects in light. He published in peer-reviewed journals. The equations held up under scrutiny. The physics community acknowledged the theoretical basis. The concept was legitimate within the framework of general relativity. Then the rebuttal came. Ken Olam and Alan Everett, physicists at Tufts University, published a response. They went through Mallett's calculations and identified the scaling problem. To produce a frame-dragging effect large enough to create a detectable closed time-like curve, Mallett's ring laser would need to be larger than the observable universe. Not a building-sized device, not a city-sized device, larger than everything that exists. The energy required exceeded anything any civilization on Earth could produce, not by a small margin, but by a margin so large that the word margin stops meaning anything. The funding collapsed. Mallett had been surviving on donations. By 2014, after decades of work, he had received a total of $11,000 in contributions. $11,000 for a career's worth of research. And the part that doesn't leave you alone is where the money came from. School children, grieving parents, people who had lost someone and wanted the machine to work as badly as he did. People who read about a physicist trying to build a time machine to see his dead father and sent him $10, $20, whatever they could, because the idea that someone was actually trying was worth something to them, even if the machine was impossible. The math works. The equations are published. The prototype demonstrated the principle. The scaling requirement makes it unbuildable by any technology that exists or is projected to exist. The universe said no in the most devastating way it can, not by breaking the math, but by making the math require more universe than there is. Ron Mallett is still alive. He's still working on the problem. He still talks about his father in every interview, after all these years, as if the conversation hasn't ended, because for him it hasn't. The grief that started this has not resolved. The physics that could resolve it will not cooperate. And every morning he gets up and works on it anyway. Every time machine on this list so far was stopped by theory. The math works, but the materials don't exist. The energy isn't available. The cylinder has to be infinite. But in September 2011, something different happened. An experiment didn't propose a time machine. It produced a measurement that implied one might be possible. A laboratory in central Italy detected neutrinos arriving from Geneva faster than the speed of light. Under Einstein's own equations, faster than light means backward in time. 174 physicists checked the result. They repeated it. They couldn't explain it away. And then someone looked at the cables. Number 6. The Opera Neutrino Experiment. The year is 2011. You're Antonio Ereditato, a physicist at the University of Bern and the spokesman for the Opera experiment, one of the largest neutrino detection collaborations on Earth. Your team spans 174 physicists from 30 institutions across 11 countries, all focused on a single measurement. The setup is straightforward in concept and staggering in execution. Shoot neutrinos from CERN in Geneva through 454 miles of the Earth's crust to the Gran Sasso National Laboratory in central Italy, and measure precisely how long the trip takes. On September 22, 2011, you stand in front of a packed auditorium and announce the result. The neutrinos arrived 60.7 nanoseconds faster than light. You understand what this means. Everyone in the room understands what it means. Under Einstein's special relativity, faster-than-light travel doesn't just break a speed limit, it breaks time. If you can send a signal faster than light, you can construct a reference frame in which that signal arrives before it was sent. This isn't a metaphor, and it isn't speculation. It is a mathematical consequence of the Lorentz transformations, the same equations that underpin every GPS satellite and every particle accelerator on the planet. Einstein himself, along with Richard Tolman and others, described the implication decades earlier. A faster-than-light signal can be used to construct what physicists call a tachyonic anti-telephone, a device that sends messages backward through time. If Opera's measurement was correct, it hadn't just broken the speed of light, it had broken causality. The global reaction was enormous. Within weeks, more than 300 papers were published analyzing the result. Physicists around the world went through the data, the methodology, the detector calibration, the statistical analysis, looking for the flaw. They couldn't find it. Opera repeated the measurement. Same result. Ereditato and his team announced it with deliberate restraint. We don't find any instrumental effect that could explain the result of the measurement. They weren't claiming time travel. They weren't even claiming they were right. They were saying they had looked for everything that could be wrong and hadn't found it, and they were inviting the entire physics community to find what they had missed. For 5 months, nobody could. Then, in February 2012, Opera found 2 hardware problems. The first was a clock oscillator that was ticking slightly too fast between synchronizations, introducing a small timing error. The second was the primary cause, and it is the kind of detail that makes you want to sit down. A fiber optic cable connecting a GPS receiver to the experiment's master clock was not fully screwed in. The loose connection introduced a 73 nanosecond delay in data transmission that was being subtracted from the neutrino flight time, making the neutrinos appear to arrive early. 60.7 nanoseconds of apparent faster-than-light travel, produced by a cable that wasn't properly tightened. The measurement collapsed. The neutrinos had been traveling at exactly the speed of light all along, just as Einstein predicted a century earlier. In March 2012, the Opera collaboration held a vote of no confidence. Antonio Ereditato and Dario Ottiero, the experiment's physics coordinator, both resigned. The careers of 2 respected physicists who had done exactly what the scientific process asks you to do: present your data honestly, invite scrutiny, publish your caveats, ended because the data turned out to be wrong for a reason nobody had thought to check. A collaboration of 174 scientists, years of work, more than 300 published papers, worldwide headlines, the most exciting result in particle physics in a generation, all of it undone by one fiber optic cable that wasn't fully screwed in. The speed of light held. Causality held. The tachyonic anti-telephone remained a mathematical curiosity and nothing more. But while experimentalists at CERN and Gran Sasso were tracing the error back to a loose cable, a theoretical physicist in Israel had already been working on something that none of the theorists before him had managed. Every time machine design on this list requires something that doesn't exist. Exotic matter, infinite cylinders, cosmic strings, energies beyond anything civilization can produce. In 2005, a physicist at the Technion Israel Institute of Technology published a paper in Physical Review Letters that eliminated the single biggest barrier to building a working time machine. His design doesn't need exotic matter. It doesn't need cosmic strings or infinite density. It works with ordinary dust. And the paper passed peer review. Number 7. Donut Time Machine. The year is 2005. You're Amos Ori, professor of physics at the Technion, Israel Institute of Technology in Haifa, and you've just submitted a paper to Physical Review Letters that does something no physicist before you has managed. The title is Formation of Closed Time-like Curves in a Composite Vacuum, Dust Asymptotically Flat Spacetime. It doesn't sound like the most important time machine paper in decades. It is. Here's the problem every time machine design had faced up to this point. Kip Thorne's traversable wormholes require exotic matter. Frank Tipler's rotating cylinder requires material compressed to infinite density, J. Richard Gott's cosmic string time machine requires objects produced in the first microseconds after the Big Bang that may no longer exist in accessible form. Miguel Alcubierre's warp drive requires negative energy density on a scale that would consume the mass energy equivalent of a planet. Every single one of these designs hits the same wall. Exotic matter, a substance with negative energy density that exerts gravitational repulsion instead of attraction. It has never been observed, never been produced, never been detected. It may not exist at all. For decades, this was the single biggest barrier between theoretical time machines and anything resembling a real one, and any physicist who wanted to dismiss the entire field could point to it and say the conversation was over. Ori removed that barrier entirely. His design uses a donut-shaped vacuum region, a torus, enveloped by a sphere of matter. By configuring strong gravitational fields in a precise arrangement around and within the torus, space-time inside bends upon itself and forms closed time-like curves, paths through space-time that loop back to their own starting point in time. A traveler moving along the interior of the donut would go further back in time with each lap. The mechanism doesn't require wormholes, cosmic strings, infinite cylinders, or warp bubbles. It requires gravity, shaped with extraordinary precision, acting on a specific geometry. The earlier version of Ori's work, from 2004, required matter with unusual but non-exotic properties, a substance that wasn't physically impossible but hadn't been identified. The 2005 paper in Physical Review Letters, Volume 95, Article 021101, went further. Ori showed that the matter enveloping the torus could be ordinary dust. Not an exotic substance, not a hypothetical material, just dust, the kind of matter that drifts between stars and settles on bookshelves. He published follow-up work in Physical Review D, Volume 76, Article 044002, in 2007, refining the mathematical framework and strengthening the result. Nature covered it. Science News covered it. NBC News covered it. The coverage was justified because Ori hadn't just proposed another time machine, he had eliminated the excuse. Every physicist who had ever dismissed time travel by pointing to the exotic matter requirement now had to reckon with a peer-reviewed paper showing you don't need it. Ori stated it plainly: the design works with matter that exists. The barrier is engineering, not physics. But there is a limitation built into the design that no amount of engineering can remove. Ori's machine can only take you back to the moment of its own creation, not before. You can't use it to visit ancient Rome or witness the signing of the Declaration of Independence. The earliest moment accessible to a traveler is the instant the machine was first switched on. Every second the machine runs, it extends its reach by one more second into the past, but it can never reach further back than its own origin. And the engineering isn't close. The gravitational fields required to curve spacetime into closed time-like curves inside the torus are enormous, far beyond anything current or projected technology can generate. The curvature must be shaped with extreme precision, because even minor deviations would prevent the curves from closing. Quantum gravity effects, which no existing theory fully describes, might intervene to prevent closed time-like curves from forming at all. And there is no engineering pathway, no prototype, no materials research program, no institutional effort of any kind aimed at producing the gravitational conditions Ori's mathematics require. But the significance of the paper isn't that someone can build the machine tomorrow. It's that Ori changed what the conversation is about. Before 2005, every time machine proposal ended with the same objection, that the material doesn't exist. After Ori, that objection no longer applies. The material exists, the engineering doesn't. And those are very different kinds of problems, because the barrier is no longer a fundamental law. It's an engineering limitation, and engineering limitations have been overcome before. If you've made it to number 7, you're clearly in this for the long haul. Hit subscribe so you don't miss the last 3. because the final entry on this list is the one I still can't fully explain. Ori proved you don't need exotic matter to build a time machine, but his design requires gravitational fields no civilization on Earth can produce. While theorists were writing papers about what might be possible, an engineer at NASA was spending 20 years trying to detect space-time distortion in a laboratory. He built equipment, he ran experiments, and in 2021, while working on something else entirely for DARPA, his team found something nobody expected. Number 8. Eagleworks warp bubble. Ori proved you don't need exotic matter, but the gravitational fields his design required were beyond anything human engineering could produce. The math was valid, the machine was unreachable. Then, inside a NASA laboratory in Houston, an engineer started trying to solve the problem from a completely different direction. Not with gravity, with space-time itself. The idea started 20 years earlier. The year is 1994. You're Miguel Alcubierre, a Mexican theoretical physicist at the University of Wales in Cardiff, and you've just submitted a paper to Classical and Quantum Gravity that does something no one in the field expected. The title is The Warp Drive, Hyperfast Travel Within General Relativity. The concept is specific, a bubble of warped spacetime that contracts space in front of a spacecraft and expands it behind, carrying the craft faster than light without the craft itself ever locally exceeding light speed. The ship doesn't move through space. Space moves around the ship. General relativity sets no speed limit on the expansion or contraction of spacetime itself, only on objects moving through it. Alcubierre's metric doesn't violate Einstein, it routes around him. The paper was published in Volume 11, 1994, pages L73 through L77, 5 pages, peer-reviewed, accepted, printed. And the reason it belongs on this list has nothing to do with propulsion. In 1996, Alan Everett at Tufts University proved that a simple modification of the Alcubierre metric creates closed time-like curves. Under special relativity, anything that travels faster than light in one reference frame can be arranged to arrive before it left in another. Faster-than-light travel doesn't just break the speed limit, it breaks causality. A warp drive is a time machine. Any functioning Alcubierre drive could be configured to send matter backward in time. The warp bubble designed for interstellar travel is, by the mathematics of relativity, a blueprint for temporal displacement. But there was a problem so severe it turned the whole design into a thought experiment. The original metric required more negative energy than the total mass energy of the observable universe. Not difficult, not expensive, mathematically absurd. Valid general relativity that demanded more energy than everything that exists. That was supposed to end the conversation. It didn't. The year is 2011. Harold Sonny White is an aerospace engineer who has spent 20 years at NASA's Johnson Space Center in Houston, Texas. He founded the Eagleworks laboratory, NASA's only advanced propulsion physics lab, a facility dedicated to ideas the rest of the agency considered too speculative to fund. White looked at Alcubierre's energy requirement and found a way to reduce it. By reshaping the warp bubble from a flat ring to a thicker toroid, he brought the energy requirement down from more than the observable universe to roughly the mass energy of the Voyager 1 spacecraft. Approximately 1,500 pounds. Still enormous by any engineering standard, but no longer a number that belongs in a punchline. White went further. He built a modified Michelson interferometer at Johnson Space Center to detect microscopic distortions in spacetime, testing whether an electromagnetic field could produce a measurable warp effect in a laboratory. The experiments ran. The results were inconclusive. But in 2021, something unexpected happened. White's team, now working on DARPA-funded analysis of custom Casimir cavity geometries, nanoscale vacuum energy structures, designed for an entirely unrelated purpose, discovered that one of their cavity configurations produced an energy density distribution matching the requirements of an Alcubierre warp field. They weren't looking for it. The geometry appeared while they were running worldline numerics on vacuum fluctuations between custom-shaped metallic plates. The paper was published in the European Physical Journal C in July 2021, titled Worldline Numerics Applied to Custom Casimir Geometry Generates Unanticipated Intersection with Alcubierre Warp Metric. The warp bubble shape was real, published in a peer-reviewed journal with measured data behind it. The structure was nanoscale, far too small for propulsion, far too small for a vehicle, far too small for anything resembling a time machine. A warp bubble confirmed in a laboratory with no path to scaling it up. White had left NASA in 2019, 2 years before the paper was published. He co-founded the Limitless Space Institute to continue the work privately. The pattern by now should be familiar. A theoretical paper in 1994, a NASA lab trying to detect spacetime warping, an accidental discovery during DARPA-funded research, a peer-reviewed publication. And then the engineer who found it leaves the institution and continues outside the system that produced the discovery. The warp bubble is real. It is peer-reviewed. It is nanoscale. And the work continues privately. Meanwhile, the Large Hadron Collider was already running. In 2011, two physicists at Vanderbilt University realized the LHC might already be testing whether a time-traveling particle existed. They published a prediction so specific that the collider's own data could confirm or destroy it. The data came in. Number 9. The CERN Higgs singlet. The year is 2011. You're Tom Weiler, professor of physics at Vanderbilt University in Nashville, and you've just posted a paper to Arxiv with your colleague Chewy Man Ho that you know is going to get attention. The title is Causality Violating Higgs Singlets at the LHC. The paper is dense, mathematical, built entirely within the framework of M-theory and the extended standard model. But the prediction inside it is simple enough that anyone can understand it. If the Large Hadron Collider, the most powerful particle accelerator ever built, produces a specific particle called the Higgs singlet, that particle will travel backward in time. Not metaphorically. Not in a theoretical limit. Actually, the singlet would exploit a compactified fifth dimension predicted by M-theory, a dimension so small it's folded into the fabric of spacetime at a scale invisible to normal observation. The singlet would travel through this extra dimension as a shortcut, bypassing the normal flow of time entirely, and the signature would be unmistakable. In a particle collision at the LHC, you produce a spray of particles at a specific point in the detector, the primary vertex. Everything radiates outward from that point. What Weiler and Ho predicted was that the Higgs singlet would produce a secondary decay vertex, a second spray of particles, that appeared in the detector before the primary vertex that created it. The effect would arrive before the cause. The instrument would record the consequence before the event that produced it. The math was clean. The model was built on standard M-theory extensions that had been in the literature for years. The particle accelerator that could test it was already running. The LHC, straddling the French-Swiss border near Geneva, was colliding protons at 7 tera-electron volts of energy, higher than any machine in history. It had the reach. The singlet, if it existed, would be within the collider's energy range. The experiment didn't need to be designed. It was already happening. Every collision the LHC produced was a test of Weiler and Ho's prediction. All anyone had to do was look at the data. Here's where it gets strange. The LHC wasn't looking for time travel. It was looking for the Higgs boson, the particle that gives other particles their mass, the last missing piece of the standard model of particle physics. On July 4, 2012, CERN announced it. The Higgs boson had been found. Two independent detectors, ATLAS and CMS, had each identified the particle with a confidence level of 5 sigma, meaning the odds of the detection being a statistical fluke were less than 1 in 3.5 million. It was the discovery the physics community had been chasing since the 1960s. Peter Higgs and François Englert shared the Nobel Prize in Physics in 2013 for predicting the particle's existence decades earlier. The discovery confirmed the standard model Higgs, not an extended version, not a version with extra dimensions, not a version that included the singlet Weiler and Ho had predicted. The Higgs boson that the LHC found was exactly the particle the standard model required, and nothing more. No singlet, no secondary vertices appearing before their causes, no particles traveling backward through time. The test had run. The answer was no. The paper is still on Arxiv. Reference number 1103.1373. It has not been retracted because there's nothing to retract. The math is valid within its framework. The framework simply doesn't describe the universe the LHC found. The collider that could have been the first time machine in history produced the data that proved it wasn't. A $13.25 billion machine, built by 10,000 scientists from over 100 countries, had tested the prediction, and the prediction failed. And that was supposed to be the end of the story. The theoretical blueprints didn't work. The exotic matter didn't exist. The singlet wasn't there. Every approach through mainstream physics had been tested, published, and stopped by the universe's own rules. But while Western physicists were writing equations and waiting for collider results, a Russian aerospace engineer was doing something none of them had the nerve to do. He built one. Not a theory, not a computer model, a physical device with electromagnetic coils that he turned on and put living things inside. He put mice in it. He measured time running slower inside the device than outside. He scaled it to human size. He founded an organization. He published results. And then, at 52 years old, he was dead. His name was Vadim Chernobrov. His machines have not been found. Number 10. Chernobrov Electromagnetic Time Machine. The year is 1987. You're a 22-year-old aerospace engineering student at the Moscow Aviation Institute, the most competitive aeronautics program in the Soviet Union, and you've just started building something in your laboratory that you can't tell anyone about. Not because the work is classified, because if you say out loud what you're building, your academic career ends before it starts. A time machine. In a Soviet engineering institute, under a government that can still exile you for ideological deviation. You call it the Prospective Space Transportation System. You file the paperwork under propulsion research. Nobody asks what you're really doing, because the name sounds boring enough that nobody wants to know. The device was specific. A nested series of electromagnetic coils, approximately 3 feet in diameter, arranged concentrically, generating converging electromagnetic waves at calculated frequencies. The theory behind it was Chernobrov's own derivation, not drawn from any published physics program, not backed by a university grant, not submitted to any journal for peer review before construction. He built it, and then he tested it, because he was the kind of person who built things first and argued about them later. The first test subjects were mice. Chernobrov placed them inside the activated device for 1 hour. When he compared the elapsed time on synchronized clocks, one inside the device and one outside, the clock inside the device had recorded 3,560 seconds. The clock outside had recorded 3,600 seconds. A discrepancy of 40 seconds. 40 seconds of missing time inside a machine made of electromagnetic coils in a student laboratory at the Moscow Aviation Institute. The methodology was not peer-reviewed by any Western institution. The instruments were not independently calibrated by an outside team. The result was documented in Chernobrov's own records, which he published through channels outside mainstream scientific publishing. Those are the limitations. The result is the result. He didn't stop at mice. In August 2001, Chernobrov deployed a human-scale version of the device in a remote forest in Russia's Volgograd region. The device was larger, more powerful, and designed for human entry. He published reports through Kosmopoisk, the scientific organization he had founded and officially registered with Russian authorities in 2004. The name means space search in Russian. On paper, Kosmopoisk investigated anomalous phenomena. In practice, it was Chernobrov's infrastructure for continuing his electromagnetic time experiments outside the university system that would never have funded them. The published reports documented time rate changes of up to 3% inside the active device. 3%. If those numbers are accurate, time inside Chernobrov's machine moved at 97% of the rate of time outside it, not a simulation, not a calculation, a measured difference in how fast time moved inside a machine built by one man with electromagnetic coils. The real question is what happened behind closed doors. No independent laboratory replicated the experiments. No Western physicist reviewed the instrumentation. No international team visited the Volgograd site. Chernobrov invited colleagues and published openly, but the geography and politics of post-Soviet Russian science meant that Western engagement was effectively zero. The work existed in a parallel world, documented in Russian, published through Russian channels, accessible in theory and invisible in practice. On May 18, 2017, Vadim Chernobrov died in Moscow. He was 52 years old. The official cause was described as a serious illness. No further details have been published. No obituary in any scientific journal, Russian or Western, carried a description of the illness, its onset, or its progression. And somehow, it gets worse. After his death, Kosmopoisk continued to exist as a registered organization, but the electromagnetic time experiments stopped. No successor took over the research. No institutional archive preserved the calibration records, the device specifications, or the experimental protocols in a form accessible to outside researchers. The devices themselves, The nested coil assemblies that Chernobrov had built and tested over 30 years are unaccounted for. Not destroyed, not donated, not catalogued, just unaccounted for. The man who built the only devices on this list that produced measurable time rate changes died at 52, and the machines, the protocols, and the data went with him. 10 attempts to build a time machine. 10 stops. A rotating universe that doesn't match reality. Cosmic strings that have never been found. An infinite cylinder no material can build. A wormhole locked behind exotic matter. A ring laser that would need to be larger than the observable universe. Neutrinos that arrived early because a cable was loose. Gravitational fields beyond any technology on Earth. A warp bubble visible only at the nanoscale. A collider that found the Higgs and nothing else. And an engineer who measured time slowing down inside his machine, then died at 52, and the research disappeared. 10 different mechanisms. A mathematical mismatch, a hypothetical object, an impossible material, a non-existent substance, a scaling problem, a hardware error, an engineering barrier, an energy requirement, a missing particle, a death. 10 different stops. The same result, every time. The pattern is the answer. Tell me in the comments which of these 10 you think actually got closest. Subscribe if you want more like this.